days we're supposed to be tackling a very simple problem by some very simple means. Okay, so it's, the first lecture was very philosophical about how you should generally behave yourself in tackling numerical things, the numerical approach. And the second lecture was about solving a key equation, the Poisson equation, which occurs in all approaches. We're actually using the stream function vorticity approach for the first lecture, and then we'll go to what's called the primitive variables, where we go back to velocities and pressures. And in both of them, you have to solve a Poisson problem. There's this difficulty of pressure, and it looks like I've eliminated the problem of pressure by using the vorticity equation. It's only half gone away. So in a simple approach, I'm just using finite differences, equispaced, and the Poisson problem is very slow, so eventually we'll need faster ways of tackling it. But for the moment, I did give one speed up, which gives you an order of magnitude speeding up, called successive over-relaxation. And then something I think is very important is that in the last lecture, and I shall continue all the way through the course, is you should test what's going on. Is it behaving as it should do? Are the magnitudes roughly what you expected from some physical intuition? Is the shape of the function, the answer, roughly right? Then we designed a code which was second order accurate. It had errors of delta x squared. Did the computer produce answers which vary between different sizes of delta x, which behaved, the answer changed by only delta x squared. So I plot the answer for various delta x's, plotting as a function of delta x squared. Do I get a linear extrapolation? So you have to test the code is behaving itself. Very typically, you can get the indexing, I goes from 1 to n, it should have gone to I, it goes to 1 to n minus 1. If you get that wrong, there'll be a first order error comes in. Right. So we're going to continue now with actually solving the float. And the first lecture this morning is on using the vorticity equation. The second equation is the original variables. So we have vorticity changes in time due to being advected around, which happens to be written in there in terms of a Jacobian, and a diffusion of vorticity. And we start at rest with no vorticity initially. And I'm going to step forward from time level n to time level n plus 1 at the interior points. The differential equation is true in the interior, and there are boundary conditions that tell you what is happening on the boundary. So they're the interior points. My indexing, I have to apologize, starts sensibly. The boundary is 0 and n, so my interior points are 1 to n minus 1. There are many common programming languages where you can't start at 0, and so you'll all be shifted along 1. So in the numerical version of this, you can see omega at n plus 1 is omega at n plus delta t times the right-hand side of that equation, and it's a bit of a mess. There are the y derivatives of psi and the x derivatives of omega, and then the other way around. And then we have our numerical molecule, which is saying that it's the Laplacian. So I take minus 4 of omega at the point ij, and then I add to it at the I plus 1, at I minus 1, j plus 1, and j minus 1. So that's how we time step the interior points, and we need a boundary condition on the boundary. For psi, when we solved how psi, we solved last lecture, how psi depends on omega, we used a boundary condition of no flow through the boundary, which is psi, the stream function is a streamline, and so is constant. Well, we need a value of omega, and that's difficult because we actually were told d psi by dn, the normal derivative of psi is the tangential velocity. Right, so this is how you can find out what's happening. So from psi on the, I'm doing the bottom boundary which is at j equals 0, and one point into the interior going upwards from the bottom boundary is j equals 1. So I can work out the horizontal velocity, which is the psi by dy, by taking psi 1 minus psi 0 and divided by delta y, which is equal to delta x. So I've got the velocity at 1/2 point in, and then if I take the velocity 1/2 point in and away from the wall, I can take the y derivative of how the horizontal velocity u is varying to get du by dy, which is the vorticity when there's not a vertical velocity on the wall. And so we have the vorticity at 1/4 point in is equal to this difference in the stream function at 1 point in and on the boundary, and the velocity on the wall, which is prescribed. On 3 of the boundaries, the velocity of the wall is 0. On the top, there's this sine squared variation of the tangential velocity. So that's the vorticity at 1/4 of a point in, and the crudest thing you can do is to say, well, therefore, the velocity, the omega, the vorticity, omega on the boundary is roughly equal to what it is 1/4 of the point in. There is a first order delta x error in that. It's not the best boundary condition. So we'll see what happens if we apply that. But we'd really like, as the code has been designed to be second order accurate, we'd like to do better than first order accurate on the boundary. And you can do that by, we know the value at 1/4, we know the value in the interior, and so you can linearly extrapolate from 1 down to 1/4 down to 0, and the extrapolation law is 4/3 of the quarter value minus 1/3 of the value 1 in. And by that, we can then get the vorticity on the boundary to second order accuracy. So I have to substitute this expression into there. I know the stream function, I know the vorticity on the interior, and I know the prescribed boundary condition. So therefore I can work out what is the vorticity on the boundary, and I need that in this del squared of the Laplacian of the vorticity. When I'm 1 point into the interior, this point j minus 1 is on the boundary. So I need the boundary values. Okay. And because the vorticity is 0 initially, but the prescribed velocity is not 0 initially, at the initial moment, you will find that this vorticity is 1 upon delta x. So this is physically, when you start the flow from rest and suddenly apply a velocity on the boundary, you have a delta function of vorticity sitting on the boundary. We can't have an infinite delta function. The numerical representation of a delta function is to have actually minus 2u divided by delta x, a very large value because delta x is small, is the vorticity on the boundary. Yes?
1/4.
A quarter, yes.
So basically, at normal velocities will be 0 at the boundary.
Yes. No, well, no, not on the top, because that's what's
Yes,
the drive.
only on the
Yeah,
right,
top,
left,
yes.
and bottom.
Okay.
And only tangential velocity will exist.
In the interior.
Yes, tangential velocity.
Yeah.
So psi will be constant. The stream function will be constant.
Yes.
Because there will be no gradient in y direction for left and right. Okay.
Yes. We used that last time. That's the normal velocity.
Yes.
Therefore, psi is constant around the boundary.
Okay. So basically, I want to know that you can go by Taylor expansion. If you span any point on the wall, bottom wall,
Yep.
and expand it for Taylor expand for next node.
Yep.
So you can get the wall velocity from there also. So I don't understand why we are doing this. As I have done the same, I did it. So I did by Taylor expansion.
Yeah, you could. Okay. So one way of finding out what the errors is is to do a Taylor series expansion, include lots of extra terms, and it will tell you what the errors are. So you should find that the vorticity on the wall, if you do a Taylor series expansion of the stream function away from the wall, will end up being the first order term is this, and this is a second order delta x squared error term.
That was we are getting the stream function above the wall.
Yep, you can do a Taylor series expansion in y, and then identify the terms. The second derivative in y is the stream function, because there's along the boundary there's no x derivatives, but once you start going up, there are x, y derivatives you have to start worrying about.
Is that
Sorry? This is an exact linear extrapolation. So if you've got a quantity, it happens to be omega.
it is not
It is not?
Richardson.
Yeah, it's a sort of Richardson extrapolation, if you like. You suppose omega is a constant a, which I don't know, plus y times another constant b. Okay? And you fit a and b to the known values at y equals 1 and y equals a quarter, and then ask what is the value of this a plus by at y equals 0. And that's the answer. So you could test that. A constant, okay? If omega was constant in y, then it'll be the same at 1 and a quarter. And then 1 minus from 4 is 3. So that's right. Now the question is, does it work when the vorticity, when omega varies with y? So what is a quarter? So it'll be a quarter at a quarter and 1 at 1. And you get a quarter, so it's 0. Okay, so it's right in the two cases, constant and linear, which is all what we're fitting to 2 points. It is the right thing to do. I can estimate the tangential velocity by, the tangential velocity is given by d psi by dy. So this is a delta y. And from 0 to 1 central differencing, so second order accurately, I get it at the point half. And then the vorticity is when dv by dx is 0, because v is 0, is equal to du by dy. And then so a quarter in and 0 in, and I have to divide by the distance between them, half delta x, I get it at the quarter point, which isn't quite the boundary, and therefore we do the linear. Right then. Okay, so there's a major problem in this, and it happens in all time-stepping codes. The things go wrong. So I'm going to show you the result for the vorticity. My Reynolds number is 10 in all of this. I've got a 10 grid points across, a strange but smallish value of delta t, and this is at time is roughly a half. And the answer is that, total mess. So there's an instability. And the big question is it a numerical instability or is it a physical instability? There's an instability in results from the code. So you have to think, physically, do you believe at Reynolds number 10 in this driven cavity, it's physically unstable? And I should very much doubt it. You've got solid do-nothing on 3 sides and a small little velocity in the middle. So I would guess normally flows go unstable at a Reynolds number of 100. In fact, because there's so much do-nothing around on the no-slip boundary condition, I reckon you actually have to go to a couple of thousand in this. That's a guess. Certainly 100. 10 has to be stable. So I don't think this is a physical instability. I think it's a numerical instability because we were greedy and we had delta t too big. Right. Another reason why I think it's a numerical instability, numerical instabilities have this pattern of jumping up and down. So it's plus and then minus. So it's plus, looks like it's about plus 50 and minus 50. Plus 50, minus 50. It's called a checkerboard pattern. That there are black squares which are up at plus 50 and there are white squares which are down at minus 50. If you see that, it's got to be a numerical instability. Right. So there's this checkerboard instability, and then we can find out something about it. Suppose we thought it was either at some time level, it's or a magnitude of amplitude an, and it's either a plus 1 or a minus 1. So if I raise minus 1 to the power I plus j, I get this plus minus. Adjacent ones are of the opposite sign, and they're all the same magnitude of an at time level n. And I can go and substitute into it's the diffusion part of the time stepping that's causing the problem. So that I'm eliminating most of the differential equation and saying the vorticity at time level n plus 1, that's the amplitude at time level n plus 1, is the amplitude at time level n, an. So an plus 1 is an plus delta t times what is our numerical molecule doing. So we have this minus 4, 1, 1, 1, 1, and we're applying that to a plus, minus, plus, minus, minus, plus, minus pattern. So what do we get? We get minus 4, and then because this is minus, we get minus 1 from that, minus 1 from that, minus 1 from that, minus 1 from that. We get minus 8. Okay, so we have minus 8 times the amplitude, and there's a divide by the Reynolds number and delta x squared we had in the differential equation that you can look at. So this is telling me the amplitude at time level n plus 1 is going to be the time level at n times 1 minus 8 delta t divided by the Reynolds number delta x squared. And if I want that to not grow, I need that delta t has to be less than a quarter times the Reynolds number times delta x squared. Right. And this is effectively saying that because the diffusivity is the Reynolds number in this the diffusivity is 1 upon the Reynolds number, that we mustn't diffuse in one time step delta t, we mustn't diffuse further than one spatial grid block. If you try to diffuse further than one spatial grid block, it all gets wrong and numerically unstable. Okay, so quarter's the critical thing, and these are my initials. I always work at 1/5. So it's 80% of the stability limit. It's dangerous to go right up to the stability limit. And just occasionally things still go wrong, so I have to come back down a bit. But otherwise I'm as greedy as possible. Okay? And there are very good reasons why you shouldn't be, you don't want to be overcautious and be a 10th or a 100th. That is a total waste of time. So you want to be fairly greedy. Okay, that was the instability due to diffusion. There are other more complicated terms in our governing equation. There is advection, moving around with the velocity. And there is a stability criterion, Courant Frederick Louis. But it's always known as the CFL condition, which is that you mustn't advect, you have to keep the time step small enough so you don't advect, don't moving with the flow, you don't go further than one grid block. So delta t is less than U max divided times delta t. That's what I've got here. So there's a second stability criterion, except there isn't really, because, right, you have to resolve the boundary layers. We've got viscous boundary layers in a fluid dynamics problem, and to make sure you have a couple of points inside a boundary layer, your delta x isn't 3 times the boundary layer thickness, so you don't see any most of the physics. You require that the grid block Reynolds number In dimensional terms, that's the velocity delta x divided by the viscosity. The Reynolds number, based on the length scale of the grid block, that has to be less than 1 if you're going to resolve delta x is small enough to resolve the boundary layers. And in dimensional terms, that's delta x is less than the Reynolds number. And if you ask for delta x to be less than 1 upon the Reynolds number, so you resolve your boundary layers, and you ask that diffusional stability here, you end up with satisfying the CFL condition. So the two stability criterion are satisfied by the same restriction on delta t as long as you've applied this restriction on delta x. Right, so how much does it cost us to make a simulation of a fluid flow up to non-dimensional time 1? Well, there's the number of time steps. We've just found that delta t has got to be less than delta x squared. So as delta x is 1 upon n, the number of time steps is 1 upon delta t, and delta t is less than delta x squared, which is equal to 1 upon n squared. So there is n squared time steps to get to time equals 1. And each time step costs us n cubed if we use the faster SOR, successive over relaxation. So the total cost is n to the 5th. So if you want to just casually double your spatial accuracy, you've got many more points in your solving the Poisson problem, and you've got to take many more time steps because of the small spatial resolution. So it actually goes up by a factor of 32, the cost. Now everyone can go from 1 second to 30 seconds. Do it again, and we're at, what is it? Oh, quarter of an hour, is that right? We can do that. Do it again, we're into a serious fraction of a day. So it's quite possible to run out of time. Another philosophical remark. It was very interesting when PCs, personal computers, arrived in the 80s, and I helped a very famous physiologist, experimentalist, set up his IBM with an analog to digital converter so he could hook his experiments onto his computer and grab the data. There weren't kits like you have these days that do it automatically for you. You had to write assembly code that I did for him. And while I was running, it wouldn't work, and while I was beavering away, he said, you know, it's interesting. He ran the famous, he was Andrew Huxley, who ran the Huxley Hodgkin equation in the early 1950s using paper tape. He said, it's very interesting. All scientific computing takes 20 minutes. The reason it takes 20 minutes, he said, is if it takes 5 minutes, you do it more accurately. If it takes more than 20 minutes, you've forgotten the question you asked the computer when it gives you the answer. So you can't have an intelligent discussion with it. So I told a big manufacturer of glass that their computer code, which took 2 weeks to run, was not an intelligent thing to do. And they eventually believed me and stopped it. I got them to compare their in-house code with commercial code for predicting the temperature inside a glass furnace. And it's 1,000 odd degrees. And the two were comparable within plus or minus 100 degrees. And they were both gave results very similar to actually an experimental lab where they'd very dangerously measured the temperature by clever techniques. The difficulty is plus or minus 100 degrees is the difference between melting glass and melting the building. So it was no use at all. Right, okay. There are better time stepping methods, which we'll get to, which allow you to take bigger time steps, so that we don't have this big restriction that we need n squared time steps. However, they're not very accurate. So it's not clear that it's good. Okay, so now we've got to, I've told you, now with my time step small enough, it works. And we're going to get some answers, but we have to think, are they the right answers? And we'd like to test we're getting the right answers. And we have no analytic solution. When I solved the Poisson problem, I didn't give it the vorticity. I gave it a very simple function, sine x sine y, where I knew the answer. Now we're solving the flow. We don't have, at Reynolds number 10, an analytic answer for the flow, so we can't test the code against an analytic answer. But we can test that it is behaving itself and that the errors are first order in delta t and second order in delta x. That may be true. So I'm going to first look at are the time stepping, which is forward time stepping, do they lead to errors proportional to delta t? So I'm going to plot the answer, some answer, as a function of delta t, and I'm going to vary delta t. I can't make delta t very big, because I've got this constraint that it's less than delta x squared. So, and I want to plot something, so I'm going to plot the vorticity in the middle at time equals 1. And I'm going to compare with different calculations, so I have to be very careful that I am exactly at the middle and exactly at time equals 1. Comparing time equals 1 and 1 plus delta t is going to be delta t different. So I have to be very careful. So that's why I have to make my delta t's 1 upon an integer in size. Right, and here's the plot. You can't read the numbers, perhaps. What you can see are some linear plots. So the top one is actually with 10 grid points, then 14, and then 20. Because I've got a smaller grid size, delta x is smaller with n is with 14 and 20, the lower points, I have to have a delta t which is smaller. The biggest, so this is the biggest delta t I can have to be numerically stable. And I've taken smaller and smaller delta t's, and you can see that, yes, the code is linearly behaving itself. So it is, as designed, delta t accurate. What you can also see, you shouldn't worry about these small delta t errors. There are enormous errors because of the delta x. The different grids are giving enormously different answers. And that is because I was using the first order boundary condition. As it says at the top here, using the first order boundary condition on the vorticity, saying the vorticity on the boundary is the vorticity at a quarter of a point in. So that crude approximation there gives you these big errors. So if I switch to the second order boundary condition, that linear interpolation we talked about, we get this, that the errors in changing delta t, as I go across the page, are similar to the errors in delta x, for changing delta x. Right, so it's well worth having that second order boundary condition on the vorticity. Okay. So we have errors which are proportional to delta x squared and are proportional to delta t. And the nice thing is this stability criterion, I'm operating not on the boundary, but at 1/5 of the boundary, that we have to have delta t the size of delta x squared, means that delta t time errors are the same size as delta x squared space errors, because delta t is the size of delta x squared. So it's quite consistent to have forward time stepping, crude first order time stepping, and second order space differencing. There's no point in having second order time stepping because your time step is forced to be small. So the first errors in doing first order time stepping are the same size as the second order accurate space errors. Okay, so there's no need for that second order time stepping. Good. Okay, so I'm actually going to test. I'm going to fix delta t to being exactly 1/5 times delta x squared, and then compute some, at Reynolds number 10, the vorticity in the middle at time equals 1 again, for various grid sizes, and you see that crudely there is a linear extrapolation of the vorticity in the middle. The crudest grid is not quite on the linear line, and actually the finest grid isn't on the linear line because there are just so many points in the calculation, things are getting a bit wrong. The real number rounding error is affecting. But I can, by this linear extrapolation, tell you the vorticity in the middle is, I've got it here to how many figures? 4-figure accuracy. Yeah. It's not 4-figure accuracy for one of those grids, it's 4-figure accuracy from the extrapolation of several of those grids. Okay. So, as it's saying here, that I can get, using the fact that it is quadratic, I'm plotting the lowest, this is delta x squared, and this is the vorticity in the middle. Because there's this linear variation, I can just actually take a 10 by 10 grid and a 14 by 14 grid there, and extrapolate those and get the answer equivalent to a 28 grid. So linear extrapolation from crude grids is as accurate as much finer grids, but the cost is very much smaller. Why isn't it linear all the way down? Okay, well the first point is just not enough resolution around. And the last point, I'm not quite sure whether I've made some mistake. I admit that I make mistakes from time to time. Or whether it is the rounding error, that real numbers are not held exactly, but only to a limited accuracy. And if you add up in a fine grid, you've got many, many time steps of many, many numbers, and eventually the rounding error hits you. So it is true, these extrapolations, as you go down, they go down beautifully linear, and then they turn up and blow up. As you get too many points, the rounding error kills you. And there's a way of estimating what's the finest grid you can calculate at single precision, double precision, quadruple precision. So this is all done in standard double precision, and not better. Okay, so we're now getting to the results. Now I've got a working code. I'm confident in it. I know that what the restrictions on delta t are. I can plot something. I have no idea. This is the vorticity in the middle still, as a function of time, and you see it drops down to a steady state by time equals 2. I'm going to, and it's 3-figure accurate it's within the steady state to 3 significant places at time equals 2. I'm going to give you all the answers at time equals 3. So I'm now running all the codes to steady state and to find out what is the answer at time equals 3, which is the steady state. Okay, it's 4-figure accuracy. Okay, just the last remark there, that we're supposed to take something like 2n iterations on every solution of the Poisson equation. So to go to time equals 1, we take n squared steps. At every time step, we're solving this Poisson problem, and we're supposed to take 2n iterations. Well, you only have to take 2 iterations in the steady state, and as you're taking n squared time steps to get there, why don't you just take 2 or 3 iterations of the Poisson problem each time step? Because eventually you will have taken enough. As long as you don't start the Poisson solver from 0, but start it from whatever you were at the last time step. So this is a cheats way, and it means time is no longer true time, it's some sort of pseudo relaxation time. But it's much cheaper. So if you're only interested in steady state, there's a point you could be economical and cut down by an order of magnitude the process. But you should really resolve the time variation properly. So you do need 2n squared iterations of the Poisson solver. Okay, so this is the result for the stream function. The bottom left-hand side is the top. I've turned it round because it looks prettier this way. So this is x going from 0 to 1 on y equals 1. And you can see that the streamlines are concentrated near that boundary. So near the top boundary, the velocities are fastest. Near the other three boundaries, which are no slip, roughly nothing's happening. They're virtually all stationary. And there, if you know about Moffat eddies, you can see right in the corner there is a reverse flow. Just in the corner here. So the flow is going around like this, and down in the corner it's going backwards. And the circulation there is 10 to the minus 6 smaller. So it's a very small circulation there. But this code nearly resolved it. That was using a 40 by 40 grid in order to, for the purpose of showing just that. Okay. The stream function is an integral of the velocity, and so it's very smooth, and nearly always the stream function is very boring. It will tell you where the flow goes, but it doesn't show you anything else. The vorticity, on the other hand, is a derivative of the velocity, and so is much more sensitive and shows you much more of what's happening. So there are much more interesting things you can see on this contour plot of the vorticity. Again, the bottom left-hand corner is the top plate going from x equals 0 to x equals 1. It's y goes from 0 to 1. So deep in surrounded by the three boundaries, there's not much happening. Most of the vorticity is on the top, and on the top it's negative. So we have this, draw it your way, you've got a top going this way, x positive, and inside the flow is slower, so you've got vorticity like that, which is clockwise, and that's mathematically negative. So you've got negative vorticity along the top because the boundary is going faster than the flow. On the sides, however, you've got flow coming down and the boundary not, so you've got vorticity this way, which is positive. And on the going up here, you've got flow that way, no flow there, so you've got, again, positive vorticity. And that's what the plot is. Okay, so you put up a plot, make sure you can see the positive vorticity, the negative vorticity. At Reynolds number 10, if you stare at the bottom picture, the contour plots, you can see there's a little more vorticity on the x equals 1 side, on the downflow side, than there is on the upflow side. This pattern of vorticity here is shifted just slightly sideways. That is, advection is moving it. So at Reynolds number 10, there is a slight asymmetry. Reynolds number 1, it would be perfectly symmetric. It's nearly perfectly symmetric here. There's just, in the vorticity, you can see a small asymmetry due to advection. And if we go up to Reynolds number 100, you'll see much more of a difference between downstream. Okay, a nice plot that I'll use is what is the velocity on the middle section. So you've got your square box. It doesn't matter, I can draw it this way. We're not the top moving one way or the other. And I'm going to cut at x equals 0. How does the horizontal velocity vary with y? So it's 0 at the bottom, it's 1 at the top in the middle. And how does it vary? And to work that out, we want the y derivative of the stream function. U is the y derivative of the stream function. So I've got the stream function at j and at j plus 1. So central differencing, I get the stream function, I get the horizontal velocity at j plus a half, the midpoint. So that's at y equals j plus a half times delta x. So I'm going to plot on I equals the middle point, and as a function of j plus a half, what is that difference? And this is the answer for a whole series of different grids at 10, 14, 20, 28, and 40. And they all superimpose on one another. So visually you can only detect errors at 1%. They're all agreeing. Why did I bother to do n equals 40 when it's the same as n equals... It's not actually n equals 10. If you look very carefully, you can see some red dots. There's one there which isn't on the line. There's a red dot there, that's n equals 10, which is not, and there's one there, which are not quite on the line. They're not visually on. So 10 isn't quite good enough. Okay, but the continuous line in very light blue, which doesn't come out very well, is for the n equals 40. Okay. And then the one quantity I wanted to calculate was the force on the top plate. How much force do I have to apply to achieve this velocity on the top plate? And that is the derivative. I've non-dimensionalized it, so there should be a mu and some lengths here. So I'm integrating across the top plate from x equals 0 to 1, the tangential, the derivative, the y derivative of the tangential velocity. So what I want, the u horizontal velocity u is d psi by dy, and so I want the y derivative of u, so I want the second derivative of psi with respect to y evaluated on the top boundary, summed across the top boundary. Now there's a problem that we don't know enough data points to work out by central differencing what is the second derivative of the stream function on the boundary. We can do it at one point in, so at j equals n minus 1, I can find out what is the second derivative of the stream function. So standard second differencing of j plus 1, j minus 1, and j. And that is second order accurate at this point. So if I crudely said that the second derivative on the boundary is equal to the second derivative one point in, I make a delta x error in that. So that's a first order accurate one. And as everything else is second order accurate, I like to be second order accurate again. And I do that by doing a linear extrapolation from the second derivative at 1 point in and the second derivative at 2 points in. Okay? And then the law of linear extrapolation is to have coefficients 2 and 1. If this quantity was constant, then I've got 2 minus 1, I've got the right answer. If this quantity varied linearly, then this would be, it would have a value 1 here and a value 2 here. So at y equals 0, the answer is 0. Okay, so this is the correct law for linear interpolation. And then if I substitute this in, I get this rather long, complicated expression, but it's second order accurate. You have to be quite careful with all these big numbers around, like 2 minus 5 plus 4 minus 1. So when you get a long expression like this, you may need to go and do this test. If psi is a constant, what does this tell me? What does this expression tell me? So a constant is 2 minus, that's minus 3, plus 4 is plus 1, minus 1 is right. I don't think I do the linear. Right, you can try. You should try 1, y squared, and y cubed. And they should give the answer 0, 0, 2, 1. 0, 0. Sorry, 0, 0, 2, 0. Ah, it says at the bottom there, sorry. When you're coding these things up, this is getting a bit complicated to type down accurately. So what I normally do is type this one in, get some answers, so I find out the force is going to be 3.9, and then I go along and put this more complicated thing in, and I find it's 3.95. So if you make a mistake in this, you get 10. or some absurd number. You get 1 upon delta x. Okay, so these are the results for the force on, and plotting the force on the lid as a function of delta x. The red curve is the first order linear law, and the blue curve is that second order. So the red curve is going to be this first order approximation. The blue curve is second order, so it's got a delta x squared. So if we plot the force as a function of delta x, I have a linear variation and I have a delta x squared variation. And from this second order accurate one, the answer is 3.9. And from these, if you can actually take these two points here and extrapolate those. So while the answer is 3.9, these grids with the first order accurate answer are sitting around about 3. That's a very big error, 30% error. Although there's a 30% error here, the linear extrapolation of these is 3.9. I do like extrapolations. So at very early times, so if we start from rest and suddenly switch on the moving boundary, what we have is a vortex sheet on the top boundary which diffuses in and gets a distance, it diffuses a distance, the square root of nu t. And so the velocity gradient is going to be 1 upon the square root of nu t. So the force on the top will vary at early times as this delta function of vorticity diffuses into the interior, like 1 upon the square root of time. I actually know the coefficient. It's 1 upon 2 pi. 1 upon the square root of pi. Sorry, 1 upon 2 square root of pi. And there's a Reynolds number in it. So as I theoretically think the force is going to behave like 1 upon the square root of time, I'm going to divide that out. So I'm not sure I believe that. That's upside down. You should multiply by it. This force divided by it, is actually the force multiplied. As a function of time, and the light blue curve is a 40, then there's 80, there's 300, 160 and 320 points. In these early times, you need a lot of points to resolve this thin boundary layer. And I'm throwing out 320 points, this is an hour's calculation or something, to find out how the force is varying in time. It is behaving like 1 upon the square root of time, so I'm multiplying the square root of time, and you see it's supposed to go to a value here of 2, I think it's 2.83 or something like that. Sorry? It's more than pi upon 3? Pi 3? No, 0 point. It's less than 0.3. So it turns out. Okay. So the reason this has gone wrong is our code was designed really for the steady state and not for very thin boundary layers. We didn't, as a very thin boundary layer here, we're not resolving it very well at all. And we should redesign the code. You should have many more y points and x points. And in fact, there's a way of having the y scale change in time, which is horrible. So it's quite a hard problem. So if you look at the purple point and extrapolate this, it's obviously nonsense initially when we don't have a delta function, we have a numerical delta function. So if you extrapolate that to time equals 0, you get to 0.33. If you take the blue curve and extrapolate it to t equals 0 carefully, I think I used a sort of quadratic fit to the points out there. I get to 0.319. And if I take the red curve and I extrapolate it down there, I get to 0.307. And then if I take these three numbers at the bottom there, 0.33, 0.319, 0.307, and extrapolate those according to delta x, to the square root of delta x, they do extrapolate exactly to 0.281. So by using lots of extrapolations, I can get the right answer. But a normal resolution of, say, 40, it is hopeless at being 0.281. Okay. Code is not designed to look at this problem. And I have to work very hard with my extrapolations to get the right answer. Okay. Are there any questions? Agreed. Okay. The remark was if you're using a higher order spatial scheme, it makes sense to use a higher order time scheme, and I agree. So there are fourth order accurate spatial schemes. Then you want to have a second order accurate time scheme if you're bound by the stability criterion. And that stability criterion is when you're going to diffuse vorticity. So in most fluid mechanics, you're interested in that resolving accurately the diffusion of vorticity. If you're not interested in resolving the diffusion of vorticity, you can take even bigger time steps by some more stable system methods of time stepping. But then you're not resolving some of the physics. Yes?
Can you please explain how the negative vorticity is generated?
How? Okay. The question is, can I explain how the negative vorticity? That's along the top, isn't it? Okay. So we have. I have to do it this way. So it goes from your left to your right. The top wall is moving like that. We start with nothing moving in the interior. So that is. Then next to the boundary, we diffuse a bit of momentum, if you like, diffuse momentum in. So we've got velocity which is higher there than here. So we've got, when we take a y derivative of u, we've got spin in that direction. Okay, spin around that, clockwise spin is mathematically negative. Negative rotation goes up anti-clockwise, so it's minus vorticity. Yes? The residue. Okay. The residue, when you're trying to solve a problem numerically, is your failure to solve the equation. So if you've got y equals some complicated expression, you take this complicated expression from your value of y and see what you got left. Oh, the escape condition. Sorry. Okay, that's not the residue. So what is the escape condition on the loop? So in all of the loops I've used, I've put an n condition, like do the iteration n squared times. I then looked at how the answer changed with the number of iterations, and I found that the Gauss-Seidel crudest original one does take 2n squared calculation. But I found the successive over-relaxation only needed 2n iterations to get four-figure accuracy. So I then actually put a stop condition on the, I would do 2n iterations. So I'm not detecting my error at satisfying the equation and using that as a stop condition. So I didn't discuss this. Yes. Right. So you can decide, you can use your failure to the residue, which is your numerical failure to satisfy the numerical equation. If you can detect how big that is, you can use that to say, I'm going to stop iteration. I'm not going to do any more iterations. But there's a major problem in doing that, is the size of the residual is not the size of your numerical error at satisfying the full equation. Okay? The size of the error is not the size. Okay. Okay. Sorry, I say it again. The size of the numerical error at satisfying the equation could be 100th or 1,000th of the size of the error of the solution. So if you have the exact numerical solution of the numerical question, which is not the exact numerical answer of the analytic question, the exact numerical answer of the numerical question, you're interested in how accurate is your approximate during your iteration. And there is a relationship between the error in the solution and the residue, which is the failure to satisfy the equation. But there is a factor difference, and it very often is a big factor difference. Okay? I know lots of codes look at the residue, and they think they've detected how big the error is in the answer. But it's not true. You have to know what the inversion. You have to know if you were to invert the operator, so you've got the solution operated, an operator on the solution is equal to the error. And so you want to know, if I invert the operator, given the residue, what is the error in the solution? And with unbounded operators, you get big numbers. Sorry. Yes? Yep.
Are we calculating b minus ax and reducing that and then escaping?
Okay. This is good, because we are solving a linear problem like this, and you get to some solution. There's some error. Okay, the nth error. And you are looking at the residual. And the question is, what is the relationship between that and that? You stop converging when that's small. You want to stop converging when that's small. And the difference is that n is A inverse residual n. So do you know the size of that operator? Sorry? Well, suppose this operator was just 10x equals b. This is 1 upon 10. So that's good, that the error is smaller than the residual. But suppose this was 1 upon 10, then your error is 10 times your residual. And the way that some matrices work, you can have near singular elements. You can have very big elements, but it all depends on the condition number of this matrix. So having termination conditions built on residues is a little dangerous. And you need to explore putting in, so if you can explore what the behavior of this operator is in a complicated problem by taking an answer at some stage and adding a bit of noise to it and seeing what's the noise you get back in the residue. And if you find there's lots of, the noise is bigger there, you've got problems. If you find the noise is small there, you're in a good state. Yes?
While checking the accuracy, we plotted, like for Reynolds number 10, we plotted DT versus the vorticity, these plots.
Yes?
These two, the first order and the second order.
Yes, yes.
So you could see that there was a much difference, but when we saw it with respect to x, that is in terms of velocity, those were pretty much on the, like, it seemed to be converged, right? So
Right. So the question is, so on this, quite coarse grids give you nearly the right answer. But here, you see a very big difference between changing delta t and changing delta x and changing delta t. Both give a big difference in the answer. But did you look at the scale? This is 0.639. This is 0.637. So it's the third figure has changed by 2 compared with 6 on the first figure. So that visually you can't see that. If I put this going from 0 to -1, these would, right. However, when you're testing that the code is behaving, you do plot on these fine scales so you can see how much it's misbehaving. I propose that I stop and find out what I'm going to talk about in less than an hour's time. Is that okay?